Again, welcome to another video on Applied Electronics. So this time I'm going to solve the quiz 1 for chemical engineering students, group B. All right, that was the second group that I wrote. Okay. So the first question was state 4 properties of a semiconductor. So here we are to state 4 properties of a semiconductor. So the first property you can state could be that for semiconductors, they tend to have 4 valence electrons, right? For example, if you take a look at silicon is having 4 valence electrons. The same for germanium, right? And these two are semiconductors. Now, the second point is that properties is that semiconductors, they tend to have a little energy gap between the valence band and the conduction band. So meaning little energy is needed to move electrons in the valence band into the conduction band. Now, semiconductors, their resistivities, right? So they tend to decrease with increase in temperature. So if you have a semiconductor, you increase the temperature, the resistivity is going to decrease as well. So when it comes to, another property is that for semiconductors, they tend to partially allow the flow of current, right? So they allow small amount of current to pass through them. And the last point is semiconductors can be doped in order to enhance their conductivity. So we can enhance their conductivity by doping. So these are some of the properties. So there are quite a lot of them, but these are just a few that you can state. Now, let's go to the next question. 1B. With the aid of diagrams, explain p-n junction. So p-n junction, when it comes to p-n junction, it's actually formed by doping one part of a semiconductor with p-type impurities, and then the other parts with n-type impurities. So as a result of this doping process, you end up having the p region having a lot of majority holes, while the n region is having a lot of electrons, right? Have majority electrons. So after a while, the majority electrons in the n region, they will start to cross the p-n junction into the majority holes, into the p region. So as they cross into this p region, they tend to lose the electrons. So you end up having a case whereby electrons are diffused into the p region. You end up having positive ions are formed along the p-n junction that is near the closer to the n region, right? And then because the p region is accepting these electrons, they tend to have negative ions. So as a result of this, you end up creating a depletion layer, meaning the area closer to the p junction become depleted of what? Electrons. So this is how the p-n junction is formed. And then now these the ions that are being formed along the p-n junction, because they are positive and negative charges, so we end up having an electric field. So you have an electrostatic field which exists as a result of the formation of the depletion region. this electric field will now prevent further migration of electrons across the p-n junction into the p region. So the energy that will now be needed to break the electric field to allow the continuous movement of electrons into the p region is what barrier potential. So that's what p-n junction is all about. Now let's move to the next question. We have question 2a. Find the forward current and forward voltage of the silicon diode as well as the load voltage with the silicon diode when the silicon diode is operating as a practical diode. So here we are talking about the diodes being operated as a practical diode. So you can see that we have figure 1. We have to find the what? The forward current, meaning that's the current that is passing through the diode. We call that forward current, right? So let's say we have here the current that is passing through the diode is forward current. And then the forward voltage. The forward voltage is the what? The same as the voltage across the diode, right? The voltage across the diode. And then the last one, we should calculate the voltage across the load voltage. You can see we have load voltage here. Okay. Now let's start with the forward current. So we look at the circuit diagram. So you can see that here we have a voltage source of 12 volts. And then when it comes to the barrier potential of the diode here, because it's silicon diode, that means the barrier potential. So we have barrier potential is going to be equal to 0.7 volts, right? So with this, so you can see here forward bias is going to take place because we have a voltage source that is connected to the diode, and that voltage source is greater than the barrier potential of the diode, which is 0.7 volts. So you have forward biasing will take place. So for forward biasing, when forward bias takes place, because the diode is going to operate or behave like a practical diode, it means that we end up getting, in this case, we have our voltage source 12 volts. Then we have our load resistance. And then when it comes to now the diode that we are going to have is going to now, the equivalent diode model is going to just we are going to have the barrier potential 0.7. Then we have a close switch here. Wow. So we have something of this nature. We have a closed circuit now. So now we can apply Kirchhoff voltage law. So with this that we have here to be 470 ohms. So we apply Kirchhoff voltage law to this. That means we end up having 12. This is going to be a drop, but the current that is passing through this is going to be what? IF. The forward current, the same current that is passing through the diode, which is here, is the same current that is passing through the load resistor here. So we have here RIF, then minus 0.7 equals to 0. So we make the forward current the subject. This just becomes 12 minus 0.7. And the load resistance is giving us 470 ohms. So I have 470 ohms. So we get here 12 minus 0.7 divided by 470. So that will give us 24.04 milliamps. So that is for the forward current, right? Now, what of the forward voltage, which is VF? Remember, we said the forward voltage for a practical diode is going to be the same as the voltage across the diode. So, which is what? The forward diode in that sense, meaning it's going to equal to the barrier potential of the diode. So, we have here to equal 0.7 volts. And then we are now to find the voltage across the load resistor or the load voltage. So we have load voltage equals to the current that is passing through, which is the forward current, times its resistance, the load resistance. So we have here 24.04 times 10 to the power minus 3 times 470. So here times 470, we get 11.3 volts. Okay. Now, these are the answers that we've gotten. So, and then this one's as well. Yes. So when it comes to question 3, right? I've explained this in the previous video. So that is um, quiz 1 for refining engineering students, right? So you can watch that video and you can get the explanation there. Now here we are to question 3B. We are to illustrate two diodes equivalent and the symbol of each type of bipolar junction transistors, right? So we are to illustrate two diodes equivalent and the symbol of each type of bipolar junction transistors. So when it comes to two diode equivalent, so the type of bipolar junction transistors that we have are, we have the NPN, right? And then the PNP, right? So if we have PNP, what that means is that we have two N region, right? And then we have one P region. Now, the two equivalent, the two diode equivalents of NPN bipolar junction transistor is going to be just looking at the two N regions that we have. You can see that here we have PN. So that PN here is going to be what? Diode, right? So NPN is just formed as a result of combining two PN junctions. So you can see here I can have PN. So if I have PN, meaning we have a diode here. So this diode with this. And now we have NPN, which is another PN junction. So we have this. So here is just our two diode equivalent. Now the same, we can do the same thing to the PNP bipolar junction transistor, meaning we have two PN region and then one N region, right? Two PN regions and then one N region. So this will also be equivalent to. So again here we can see that we have here, we have PN. So that means I can have this here. And then PN, and now you can see that I have what? NP, or you can say PN as well. So meaning PN. So this becomes the two diode equivalent, right, of this PNP. Now let's talk about the last aspect of this, which is N2 and the symbol of each type of bipolar junction transistor sisters. So for this, when it comes to the symbol for what, let's say NPN, right? Or even for PNP, just going to be, so we have two of them here. And now I'm trying to indicate the symbol. And then this one too, the symbol will be the same. So I'm just making two symbols. So we have these two here. And then let me make the line. Now, so now the difference is just going to be the current direction in the emitter terminal, right? So here, let's say this is our emitter terminal. I'm going to indicate the current direction. So if you indicate the current direction to be leaving the base here, right? Or here you can say to be leaving the emitter in that case. That means we refer to this as NPN. So this is a symbol for NPN. And then when it comes to PNP, that means the current here, the current is entering the emitter, or you can say it's entering the base here. So we have referred to this as PNP. Then we can even go ahead. Once I know here's the emitter, that means I have the base here. So I can indicate the direction of the current in the base. This with the direction. The collector is also here. Here we are going to base current and the collector also. We have something like this as a symbol. Okay. So we've come to the end of this question. So I will see you again in the next video. Bye bye.